Okay, welcome back to the afternoon session. This afternoon we have two talks, 45 minutes each. The first talk is going to be by Andrea, which is a PhD student in Torino. And he will talk about light bootstrap for multi-point defect correlators. Please, Andrea.
Thanks, Francesco, and thanks also for Andrea for giving me the opportunity to talk today. I'm very pleased to be here in Madrid. So today, as Francesco said, I will talk about light bootstrap for multi-point defect correlators. This is a work done in collaboration with Lorenzo Bianchi and Lorenzo Quintavalle, who is also here in the audience. And this is based on a recent paper that came out 2 months ago. So the plan of the talk is the following. I will start by giving some introduction and motivation on defect safeties in general and light bootstrap techniques. And I will focus on the particular case of a background two-point function. Then I will move on to the central part of our works around multi-point defect correlators, and I will show you how we bootstrapped the specific case of a background defect three-point function. I will then conclude with some concrete application of these analytical bootstrap techniques for n-equal 4 superdimensional dimension in the presence of a Wilson line, and then I will show you some future direction. If you have any question, feel free to stop. So to start, let me say why we are interested in conformal defects. First of all, they are ubiquitous in physics. They can appear as boundaries and interfaces as two-dimensional one defects. We can have impurities in spin system, Wilson lines and superconformity theories, twist operators for computational intermagnetic, and so on and so forth. For energy physics in general, they are also interesting because they can be engineered graphically. We have a dual holographic interpretation of these conformal defects in terms of probe rays or strings. And they also, these objects are no-local excitation, so they probes no-local physics. Indeed, defects couple local bar dynamics to lower dimensional figures. But for our purpose, defects are interesting because they are frequently applied within the conformal bootstrap problem. So the main idea behind the conformal bootstrap is to constrain the dynamics of a general safety using just symmetries and internal consistency. So to be clear, let me take, for example, the case of a four-point function of four identical scalar operators. This correlation function is not kinematically fixed by conformal invariance, and it can be written in terms of a function of true conformal cross ratio by using the operator product expansion to pairs of these operators. So we have different channel decomposition, and these different channel decomposition are related via a crossing equation. And the idea of the bootstrap to solve this crossing equation to extract some relevant coefficient, which are collectively called safety data. And these include the OP coefficient, the four-dimensional operator, and the spin of the operator that are in respect. One of the most important achievements in analytic bootstrap is due to a couple of seminal papers back in 2012, where they found that every safety, unitary safety with twist gap must contain an infinite tower of double twist operator at large spin. So it is that the conformal dimension is the one of GFF-like operators at large spin. And this results was obtained by looking at a specific kinematic limit, the light band limit. And this technique also unveils a universal sector at large spin. So one in general can perform a systematic large spin expansion. There are a lot of papers in that. But conformal bootstrap and light bootstrap in general can be applied not only to the four-point function, but also to higher point function, to five-point function, and six-point function. Indeed, this type of correlators give access to a larger set of safety data, like, for example, OP coefficient involving spin operating with triple twist operators. But the analytic bootstrap techniques have been applied also to the case of a correlation function in the presence of a conformal defect. And the most famous example is the application to the case of a bulk two-point function. And what we did in our works was to combine these two last points. So we wanted to extend these light bootstrap techniques to higher point correlation function, but in the presence of the defect. So let me first review a little bit of defect safety in general. As I said before, conformal defects are no local excitation, which breaks partially the conformal symmetry. So from the original conformal group SD plus 1,1, we have the residual conformal group along the parallel direction to the defect times the rotational group in the orthogonal direction. Here P is the dimension of the defect, and Q is the dimension. So in general, once we introduce the conformal defects, we have two different classes of operators. We have the usual bulk fields, which are labeled by the conformal dimension of the spin, and this operator leads to the representation of the original conformal. But now we also have some defect spins, which we call the phi-hat, which are labeled by the conformal dimension, the parallel spin, and the transverse spin. And this operator lives in the representation of the conformal group preserved by the defect. So the idea is that once we have two different classes of operators, we can construct different correlation functions in the presence of the defect. And the first simple example is the one-point function, which is a non-vanishing one-point function, kinematically fixed by conformal invariance, up to a specific coefficient, physical coefficient of 1.0 coefficient. Then the other possible correlation function we can construct in the presence of the defect is the bulk defect two-point function, which is again kinematically fixed by conformal invariance, up to this bulk to defect OP coefficient, which is related to the fact that now we have a new convergent notion of the OP. We not only have the bulk OP, where we take two operators, bring them together, close together, and expand in terms of local and bulk operator. We also have this notion of a defect OP, where we take one bulk operator and we bring it this close to the defect and expand in terms of defect operators. And so this is called the defect OP channel decomposition. So in general, we have a new class, a new collection of CST data that we can explore, containing the dimension of the operator in the defect, the one-point function, the bulk defect two-point function, and also the OP coefficient inside it. And these CST data are actually related to the usual bulk CST data via some crossing equation. So the idea of the form of bootstrap is to use the crossing equation, solve this equation, and extract this new CST data in terms of the known ones for the bulk channel. Okay, before tackle the main part of my talk around multi-point correlators, let me first review also the case of the bulk two-point function. This is the first example in which the conformal symmetry is not enough to fix kinematically the cross ratio, the correlation function. In this, if we consider two bulk scalar operator, this correlation function can be written in terms of a function of two conformal cross ratio that we call Z bar. And this can be understood geometrically in this specific conformal frame, where we fix the defect in the origin. We have the two bulk operators that lie in this transverse plane with respect to the defect, and with some light coordinates Z bar. Here we're working with Lorentzian signature. So Z bar are real independent variables, which has value between 0 and 1. And also, let me say that we are considering a space-like defect, so the time directions only contain this plane. So for this type of correlation function, we can exploit the OB for the bulk OB and the defect OB. The bulk OB gives us the so-called bulk channel. So the reduced correlator G is expanded in terms of the sum of some conformal blocks, which are labeled by the conformal dimension and the spin of the operator exchanging the bulk. While for the defect channel, we employ twice the defect OB to the bulk operators, and we can write down the reduced correlation function as a sum of this defect conformal block, which are labeled by the conformal dimension of the operator exchanging the defect and their transverse spin. Here we do not have a parallel spin because we have some scalar operator in the bulk, so we don't have a parallel spin here. And for the case of a defect conformal block, this function are actually known in full generality in terms of product of two geometric functions. So there is a closed formula for this conformal block. And the idea is that these two expansions are related to a crossing equation, and to extract some relevant CFT data, one usually takes some limit inside this crossing equation. And one useful limit is indeed the Lightcon limit, or the bulk Lightcon limit, which corresponds to taking one of the two bulk operators to the Lightcon of the other. And this in the cross ratio means taking Z bar to 1, for example. And this type of kinematical limit gives us access to some analytic information on a new family of operators, which are called double twist operator, or the analog of the double twist operator for the case of the two-point function in the presence of the defect. So for the bulk channel, this Lightcon limit tells us that the bulk conformal blocks are organized in terms of the twist. So the leading contribution in this Lightcon limit in the conformal blocks comes from the lowest twist exchange operator, which for the bulk channel is just the identity. So for the bulk channel, the Lightning limit and leading border is reduced just to some prefactor, while for the defect channel, we need to reproduce this singular behavior in the Lightning limit. And to do so, we need to look at the specific sector of the spectrum, of the defect spectrum, which is the large transfer spin spectrum. To see this, why this is the right section of the spectrum that we need to look at, we can employ this Casimir trick. And what is this Casimir trick mean? We basically take the quadratic Casimir operator of the orthogonal part of the conformal group and act on both sides of the crossing equation. So for the defect channel, the defect conformal blocks are actually eigenfunction of this quadratic Casimir operator. So we just have some eigenvalues which scales as the square of the transfer speed. While the action of this quadratic Casimir operator on the other part of the crossing equation, so on the bulk channel where we exchange the bulk identity operator, we have some divergent B contribution, which scales as 1 over 1 minus the bar to the power of 2. And the idea is that we can apply this quadratic Casimir equation at an arbitrary number of times, obtaining an arbitrary divergent behavior on this side. So we need to impose that the transfer speed must scale in as a 1 over 1 minus the bar. So indeed, the sector that we are looking at is the large transfer speed spectrum. And for the defect conformal blocks, therefore, we needed to take the Lightning limit at bar 1, but also this large speed limit, which reduces the defect conformal blocks to a very simple expression, which is some powerless expression of the constraint z times this exponential, where the exponent is kept fixed. So in these limits, the crossing equation reduces further, and we can approximate the sum over the transfer spin as an integral, since we are looking at the large transfer speed spectrum. And we just need to sum over the alpha transverse twist in this case. To simplify the analysis, we can take an additional limit, which is z to 0, and this is called double vertical limit, because we are not only taking this to the Lightning of the other bulk operator, but we also bringing this to the Lightning of the defect itself. So this is double Lightning expansion. And by matching power in Z order by order, we fix the defect spectrum of the operator that are exchanging defect channel. And this is the half transverse twist, which tells us that the family operators that are exchanged are this one, which are called transverse derivative operators, which are the analog of the usual double twist operators that appear in the case of four-point function. The difference is that now this is not a double twist, it's more like a single twist. And here the label M is controlled by the expansion in Z to 0, and it's just you can see this as an application of some orthogonal box to the external bulk operator. By bringing this information back in the crossing equation, we can perform the integral in the transfer spin, and we can solve the equation to extract this relevant safety data, which is the bulk to defect coupling between these transverse derivative operators and the external bulk field, and this is just some power law in the transfer spin. Obviously, this was done at leading order in the twist in the bulk channel. So in theory, one can go further and consider subleading twist bulk exchanges and obtain new instant asymptotic correction. But for the case of a bulk point function, similar to the case of a 4-point function, there is actually some techniques that are more powerful than asymptotic in spin, because there is actually analysis in spin. So in theory, there is a Lorenzo inversion formula, which is a more powerful technique if you want. But I will not talk about Lorenzo inversion formula for the rest of the talk. It's just to be precise that there are more powerful techniques at this case.
Sorry, question. Is there anything interesting when phi hits the Lightning of D?
When phi hits the Lightning of D first,
Yes.
Yeah,
Do you get some interesting results?
Yeah, it's something that we are currently working on another project. So you say that we take first the defect Lightning limit and then expanding the other bulk Lightning limit. So yeah, the difference is that you're changing the roles of the conformal block and of the channel, in the sense that For this case, you can see the bulk channel as the direct channel and the defect channel as the cross channel. So the idea is that if you take first the defect type limit, you are taking the defect channel as the direct channel. So in that case, we must look at the distribution that comes from the identity exchange for the defect channel.
Okay.
And this must be reproduced in the bulk channel by looking at the large spin in the bulk channel, but large total spin, not the large transfer spin. So it's the other way around if you want.
So but then it will be, it's a bit surprising because you will find that the P in the bulk knows about the defect.
They are related, no? The safety data in the bulk and the safety data in the defect. But the relation is between in this case, between the transverse derivative operator. But these transverse derivative operators are not the ones that will show up in the other case that you are mentioning.
Yeah, but these are defect operators.
Yes, the other are bulk operators. We would have the identity exchange in the defect channel. We would have double twist operator on the bulk channel.
But the new data is the one-point functions.
Yeah.
Double twists. So that's it, you don't know if you don't have a defect.
Okay, I understand. Okay, that's.
Yes.
Maybe I can also ask a clarification.
Yeah.
Just a basic confusion. I mean, I can think of this 2-point function as a 3-point function.
You can speak more like a 4-point function without the defect.
4-point function without the defect. But then what in that language, what's this transverse derivative operators?
It's the answer of the double twist operator that appears in the 4-point function if you want. Like in the 4-point function, you would have like this.
By the number of operators, when you are just at one instead of you say taking x1 to 0.
Yeah, because we have just one, but this is the same for both the operators that are brought to the defect. No, these operators live in the defect. No,
Right.
and we have two of them, but they are equal for the case of a bulk function. They must have the same control dimension and the same speed. I will show you later. For our case,
Actually, I think that you should write there the identity or something on the right hand side. The identity derivative is box.
here is just a schematic way to write down this operator. Actually, there are some other attempts that make this like the primary operators.
Right.
Just to be clear. But this is like the same operator that exchange for both bulk operators. I mean, later maybe it will be clear in the sense that for our case of bulk defect 3-point function, when we perform the defect OP, we have two different defect operators that are exchanged. But here, since we have a bulk 2-point function, once we bring one operator in the defect, the other one must be the same because we reduce it to a 2-point function in the defect. So we have.
I see. Okay. So yeah.
Okay, so now I can talk more about the core of our works, which is on multi-point defect correlators. So once we introduce the conformal defects, we have a plethora of different configuration we can imagine for higher point function. We not only have like the 5- and 6-point function that one have for the homogeneous case. So for example, the most simple correlator one can construct is the bulk defect correlators. This is not really a higher point function in the sense this depends on just one conformal first ratio. And also for us, it's not very useful because it does not have a crossing in the sense that if I perform the OP between the two defect operator and I perform the defect OP of the bulk operator, I would obtain the same type of safety data. So it's not really useful for a booster computation. The next possible configuration is the bulk defect 4-point function. And this is an higher point function because it depends on free conformal cross ratio. So you can see this as an intermediate step between the 4-point function or the bulk 2-point function in the presence of the defect and the 5-point function. Not because the 5-point function, we have 5 cross ratio. You can see this as an intermediate step. But since we're interested in probing some new safety data that relates the bulk degrees of freedom with the safety with the defect degrees of freedom, this correlation function is not really useful for us because there is only crossing inside the defect. So the first really interesting example is the bulk defect correlation function, which is the main topic of our work. Okay. So this correlation function, let me say that we consider a general d-dimensional CFT with a p-dimensional defect, flat defect, space-like, and we consider two bulk scalar operator and one defect scalar insertion. This correlation function, again, is not fixed by conformal invariance and can be written down as a function of free conformal cross ratio. We have the same cross ratio as before, z bar, which in this conformal frame describes the same type of behavior as before for the bulk two-point function. It's just the coordinates of this bulk operator inside this causal diamond. But now we have an additional conformal cross ratio, which we call S, and we can interpret this additional cross ratio as the distance between the defect insertion and the transverse plane where the other two bulk operators lie. And once again, we can apply to this reduced correlator the bulk OP and the defect OP, obtaining two different OP channel decomposition, but they act basically in the same way as before for the bulk two-point function, because this external defect operator is just a spectator from the point of view of the OP. Indeed, for the bulk channel, we just perform the bulk OP between the two bulk operators, and we exchange some bulk operator. The only difference is that now there is more complexity to this crossing equation in the sense that we have more label attached to this equation. For the bulk channel, for example, we have to sum over the dimension of the spin of the exchange operator, but we also have an additional label n, which describes the possible exchange of the tensor structure from this bulk to defect two-point function. And this additional label is mirrored, if you want, in the other channel by the fact that now the two different defect operator can be different. So we have to sum over delta F1 and delta F2. So this is the main difference between the case with respect to the case of a bulk two-point function. Here they just share the same transfer spin because we have just a scalar insertion here. So we have the same OP channel decomposition, and another feature about this crossing equation is and this difference with respect to the case of a bulk two-point function is that now we do not have bulk identity exchanges because the identity is not coupled to a general defect insertion. So this is the main difference. And the crossing equation is in a general form is this one. And just want to point out what are the safety data that enters in this crossing equation. So on the bulk channel, we have the usual bulk OP coefficient. And now we have a different safety data. For the bulk two-point function, we had the bulk one-point function. Here we have the bulk defect OP coefficient, which we have some dependence on the tensor structures. While on the defect channel, we chose a different basis. Instead of summing over the conformal dimension, we sum over this quantity that is half the transverse twist. But anyway, the safety data that enters in this channel are the bulk defect OP coefficient and the 3-point OP coefficient inside the limit. So now this is a crossing equation, and we want to exploit the Lightning booster techniques. So to do so, we need to look at the limit of z bar is equal to 1. So for the bulk conformal blocks, for this case, they are not known. So one way to obtain the bulk conformal blocks in the Lightning limit was to use the Lorentzian OP integral formula inside the correlator, which is just this integral. And this gives us an integral of a bulk defect two-point function, which results in this Lauricella function, which is you can see this as a generalization of an hypergeometric function of three variables. Here, just for reference, this is the integral representation. This is the series representation. And even though this is like not a very nice bulk conformal blocks, there are some nice features about this expression. And in particular, the part depending on the z bar 1, because once again, the Lightning limit, the leading version comes again from the lowest twist exchange operator in the path. The only difference is that now we don't have the identity. So our assumption is that the theory have a twist gap, and we assume that there is a single bulk leading twist contribution O star, which has a conformal dimension different from 0. Okay. For the defect channel, instead, the defect conformal blocks are quite surprisingly known in full generality, and they're written in terms of an upper function F4 times some Gegenbauer polynomial. And a nice feature about this defect conformal block is that the orthogonal part of this block, the Gegenbauer, is the same one that appeared for the Barth function, for the defect conformal block of the Barth function. And this is a hint that maybe, and this is something that we are currently working on, that we can construct some Lorentzian inversion formula for the defect channel in some dispersion relation, because this is like related to the fact that for the Lorentzian inversion formula, the CFT data are related to an integral of discontinuity in the plane where this term enters. So this is just a nice feature, but I will not talk about in detail. So just to say, is some nice property attached to this. Anyway, once again, we need to reproduce the singular behavior of the bulk channel in the defect channel, and to obtain this, we need to look at specific sector of the defect spectrum, which is again the large transverse beam. And to see this, we applied the same techniques that I showed you before. So the Casimir trick, applying the quadratic Casimir operator to both sides of the Pearson equation. So same thing as before. Rewriting these defect conformal blocks in terms of our cross ratio and performing the large spin limit and the Lightcon limit is the form of the defect conformal block that we are interested in. And you can see that there is still this exponential term, the exponent kept fixed by taking the limit appropriately. And the idea is that if we insert this defect conformal block back in the crossing equation and we integrate over the transfer speed, we must reproduce the original Lauricella function in the channel. So the crossing equation in its full form is this one, which can be a little bit intimidating, but there are some nice things about this. In particular, the Z-bar dependence. If we match these terms, we can fix transfer spin asymptotics of this circulator, this product of this OP coefficient, which is just some power law in spin times this unknown coefficient. So the only thing we need to fix to solve the crossing equation to boost up completely our theory is to compute this coefficient and also understand what is the spectrum of the operator exchange in the channel. So in other words, what are the twists we need to sum over in this channel to reproduce the left-hand side of the crossing equation. And the crossing equation is still like very difficult to solve in this Lightcon limit. So what we did was to take additional limits. So we take the defect Lightcon limit, which is again it's z to 0, and also the large separation limit with this hierarchy. And the idea that at leading order in the defect Lightcon limit, the crossing equation simplifies a lot, because the original Lauricella function simplifies to just an up and left one function, or even more, since this is a negative integer parameter, this is just a finite sum of some hypergeometric function. While for the defect channel, this is a very simple result. And by matching in both sides the power in Z, we can already fix the spectrum of the defect exchange operator, at least of one of the two defect exchange operators. And we recover the same transverse derivative operators that appears for the case of a Barth-Chopin function. The difference here that there is this label 0, which is related to the fact that we are looking at the leading order in the defect Lightcon limit. If one perform a computation where he looks at subleading contribution, he reproduces the same towers and operators that appear for the Barth-Chopin. Then, by matching instead the other cross ratio, so the power in 1 over x, we can fix the other exchange operator in the defect channel, and we discover this new family of operator, which we call bulk defect double twist operator. And you can see this bulk defect double twist operator as a double twist of what? Of the transverse derivative operators with the external defect operator. So because these are different operators, so this is a normal double twist operator that you would have in a homogeneous CFT. And here M is controlled by the power in 1 over x. And here we have all the tower, because we are looking at all the orders in 1 over x. And this, you can see this as the application of some parallel box to the transverse derivative operators. By putting this information back in the crossing equation, we mentioned that all the order is 1 over x. we solve the Gaussian equation and we extract this coefficient C, which relates the transverse derivative operator with this new family of operators, the bulk defect double twist operators. And this is a very nice closed formula because these are some finite sum in the tensor structure. Before moving on and show you the other limits that we consider, let me first say a little bit more about the interpretation of this new family of operators. So this bulk defect double twist operator meets bulk and defect degrees of freedom, but this operator, they are not something strange. They actually appears in the GFF spectrum. And you can see this by considering the 4-point function inside the defect, where you consider two phi-hat operators and two transverse derivative operators. And if you perform the same Lightning bootstrap analysis inside the defect of this 4-point function, you realize that on one channel you have the identity exchange, and to reproduce the identity exchange on the direct channel, in the cross channel you need to sum over some specific family of operators, which are the double twist operator, which are exactly this double twist operator that we found. But another feature of this operator that they do not couple directly to the bulk defect theory, in the sense that the bulk defect 2-point function in free theory between this double twist operator and the external bulk field is identically zero. So the interpretation that we have is that terms we are probing in this limit, we can consider them as leading order perturbation away from GFF. So the new piece, the new relevant piece of safety data that we compute is exactly this as a correction to GFF, which couple the external bulk field with the double twist operator on the defect. And on the right-hand side, the safety data that appear at the denominator are known. This is from analysis of bulk 2-point function, and this for a 4-point function inside the defect. So the only thing that we need to compute and extract are the coefficient that we call C, which is the coefficient that we obtain by solving the Gaussian equation. So this is just to give a nice interpretation of what are these operators.
Is it always phi-hat is the identity?
If phi-hat is the identity, we recover the usual case of bulk 2-point function. Yes, indeed. Yeah.
And you can add, I think, these more phi's. So
Phi-hat or phi?
phi-hat.
Yeah, indeed. As I will show you in a moment, once we consider another different hierarchy in the limits, we found a different another family of operators, which we call triple twist, in the sense that they are double twist of the double twist itself with another phi-hat. So in that case, we have more phi-hat that appear.
So isn't the phi-hat expansion a twist expansion or part of it?
What do we mean by phi-hat expansion?
So can I have operators with a 1, 2, 3, or 9 phi-hat?
Yeah.
According to the number I have.
I mean by as external operator then, because as external operator is different.
Call it as you like. So
I mean here.
What is your definition of twist?
The twist is the sorry, maybe I didn't specify, but the twist is the difference between the control dimension and the spin of the operator. So here is I will show you
Okay,
this.
the same, so it's the same definition we have dimension minus spin.
Yeah. But this correlator is not related to the one that we studied. It's just an example to show you how this type of new family appears in GFF by looking at the 4-point function inside the defect. But in general, we only consider the case of one external defect operator, phi-hat. Yeah.
Not. No, other people.
No, is what we have done. I mean, obviously, as I showed you before, there are a plethora of different operators that we can study. There is also the case of a bulk defect operators.
Is leading order in some hits. Triple will become sub-leading order in some hits.
Now we have, my case, similar expansions, this twist expansion. Now, of course, when I increase the twist, we have also derivative operators, transverse operators, we see that we have.
Yeah.
And so we call them, this stuff with the transverse parser kinetic operators.
Okay.
while the product operators, we call them genuine contribution, genuine operators, because they are no derivative in the middle.
I see.
Okay. And they have quite different properties. So the kinetic stuff come from equational motion or variable maintenance side that in principle, or at least we try to sum them at the order of derivatives much as we can, so that we can absorb them into some coefficient.
Okay.
Well, the general operators, they cannot be absorbed in anything. That's operator that should be evaluated. So I wonder if you can sum this kinetic part, this part of the derivative into some factor and some limit. Is this the message that we're telling you? So what is this factor? It's C or B?
C is just the redefinition, if you want, of the product. Should back here. When we match the Z bar dependence in the cosine equation, we redefine this, factorizing the scaling part with respect to the transverse derivative, the transverse spin S, and this is just some coefficient, which is some number basically. But it contains information about the product of this safety data. So once we found this, we found the product of this safety data.
In some sense, one of the statements we make here is that if you sum over this family of operators, you reproduce something which is effectively another operator in another channel.
Yes.
The composition of this correlator. So it's like, yeah, you're getting this whole family of contributions. They actually are related one to another. The way you can repackage them is by seeing them as the exchange of just one operator in another.
Yes, but what is interesting is the result that you get at the end. So as you have a submission operator, there is some operators and some coefficient in front of it, but this coefficient is so everything has a physical information, but probably this part of the coefficient is the most important physical information that is. Because having the final operator is easy.
Yeah.
The initial one is also easy, but difficult is to have all the design stuff in the middle, and this can give a bit of direction for this layer. Yeah. I'm not an expert in PSC, just to infer something. So,
Yeah, maybe we can discuss later.
Yeah,
probably the reason. So, yeah, the other simplifying limits that we consider is just a different hierarchy in the limits. So instead of taking first the different like limit at leading order, we take this large separation limit at leading order, or 1 over x that goes to 0, and then we take z to 0 at all the orders. And in this limit at leading order, the crossing equation simplifies even further. So, for example, on the back channel, we just have some hypergeometric function, and also we do not have a dependence on x anymore. And the tensor structure dependence is confined in the product of this safety data. For the defect channel, this is just some polynomial in the 2-cross ratio. So this is a very simplifying limit. And indeed, by matching the power in x, we already have this twist additivity for the part that here we do not have x dependence. If we perform then a geometric identity and expand at all orders around the defect light limit, we found a new interesting result with respect to the other simplifying limit, in the sense that now there are two families of contribution that appear at the same time. We not only have the case as before where we exchange the relative operator and the double twist operator, but also now there is another contribution where we exchange a double twist operator and the triple twist operator. So these two families of contribution appear at the same time, the same order. So this is something interesting, something new. Anyway, inserting this information back in the crossing equation and expanding in the different electron limits at all the orders, we were able to extract the data for both families. And this, let me say another thing from moving forward, is that here the label M is associated now to parallel orthogonal boxes, because we are looking at all the orders in the different line limit. So you can say that the expansion in X controls the application of parallel boxes to the operators, while the expansion in the different line limits in Z0 controls the application of orthogonal boxes. So this label M is related to this box. Anyway, we obtain this coefficient, which relates in this case, the transverse derivative operators with double twist, and also the double twist with the triple twist. And these are just a closed formula valid for at leading orders for the bulk life limit and the large separation limit, and at all the orders in the different line. So let me then conclude with some concrete application of this.
The triple twist is still kind of a double twist.
It's a double twist of the double
Of the
twist
double
itself
twist.
with the external defect operator. Yes. Yes. As you can see here, this phi hat is the external operator, and this phi hat phi capital phi is the double twist. So let me consider as a concrete example the case of an equal 4 superenlist for dimension in the presence of a superconformal line defect, in particular the 1/2 BPS Manda-Wilson line. First of all, this superconformal defect breaks the original superconformal algebra, which is PS2 2,2/4 down to OSP4*4, whose bosonic algebra contains SL2R, which is the conformal algebra along the line. We have SO3, which are the rotation transverse to the defect, and we have SO5R, which are the preserved R-symmetry, which is the preserved R-symmetry algebra. And in this couple, we want to consider again the bulk defect reconstruction. So for the bulk insertion, we consider 1/2 BPS chiral primary operator. This operator has some protected dimension, in this case equal to 2, so we are choosing the 20 prime operators. And they are the super primary of the strength tensor supermultiplet. Phi is one of the 6 scalar operators that appear in Lagrange of the equal 4, and Y is a complex vector polarization that projects the scalar operators in the symmetrical traceless representation of SO6. And there are a lot of papers that build operation function out of this operator. But what we are interested in, as I said before, is the bulk defect operators. So we need to consider an additional operator in the defect, and the most natural choice for us was to consider the tilt operator. This tilt operator has some conformal dimension vector equal to 1 in this case, and it appears as a super primary of the displacement supermultiplet. And in general, for any CFT that breaks some global symmetry, there must be some tilt operator. In this case, is related to the fact that we are breaking the original SO6 symmetry algebra down to SO5. So we have 5 of these operators, 1 for each of the broken generators. So this is the operators that we want to study, for which we want to exploit the light industrial techniques. And for this reason, we are not really interested in the full analysis of this correlation function. So we are not looking at the superconformal blocks or superconformal loaded entities. We just want to exploit the bulk B, in particular the super selection rule for the fusion of the 2 chiral geometry operators, the O20 prime. And this is like the super selection rule is known from the literature. Here is the short, and B is the short supermultiplet, 1/2 BPS short supermultiplets. We have the identity exchange, again the stress tensor multiplet, the 1/4 BPS short multiplets. C are the semi-short, and A are the long multiplets. But among these, we are only interested in the ones, the supermultiplets that have a non-vanishing bulk defect 2-point function with the tilt operators. So among these supermultiplets, the ones that we are looking at are the one in red here. And among these, we just need to look at the leading contribution that comes from taking the light limit in the bulk. And this comes from the lowest twist exchange operator. So we can just consider basically the leading contribution coming from this stress tensor multiplet, which has fixed twist equal to 2. So we just need to apply the same light industrial techniques to the case of a fixed dimension 2 bulk scalar exchange in the bulk channel. So we fix the tensor structure equal to the label attached to the tensor structure equal to 0. We fix all the external conformal dimensions and the conformal dimension of the operator exchange in the bulk, and this is just a result of the crossing equation of leading orders in the Latin limits without taking additional limits. And this is already a really simplified expression with respect to the one that I showed you before. First of all, let me say that we have the two family of contribution that I showed you before. So we have the translative operators and the double twist operator, and here we have the double twist and the triple twist. And also in the bulk channel, we can see that there are two independent pieces. One which includes integer power of z, the other which includes half integer power of z. And this is reflected also by the fact that the half integer power and the integer power in z, they are separated also in the other channels. So in theory, we can study these two contributions as independent pieces. So we have basically two different crossing equations, very simple crossing equation that we can study, we can simplify. In particular, by taking these two different crossing equations, by performing an expansion of all the orders in 1 over x and z, we extracted the relevancy of the data for the both families. And here, since we are at all the orders in 1 over x and z, we have two different labels attached to the double twist and the triple twist, meaning that we have both parallel boxes and orthogonal boxes applied to the operators. And this is a very nice formula to also. So, to conclude, let me say that these left and bootstrap techniques are well suited for multi-point defect correlators. We found in particular that there are two new twist accumulating families of defect operators at large spin, this double twist and this triple twist, and we found their defect safety data. So we found this closed form asymptotic expression, in particular for the case of an equal force square with the defect line. So one possible future direction would be like, can we go beyond asymptotics? Can we build a Lorenzo equation formula, like for the case, analogous for the case of a bulk function? And this is actually something that we are currently working on. Or another possibility is, can we extend this systematic approach to more involved multi-point operator function, like the one that I showed you here? The answer, I think it's yes, I think we can. And in general, this is, I think it's a better way to approach higher point function with respect to the homogeneous safety case, because the complexity in terms of the number of cross ratio attached to these correlators grows at a slower rate with respect to the ones in the homogeneous case. So in other words, this particular correlator is simpler than a 5-point function, as well as this correlation is simpler than a 6-point function. So this is something that it can be looked at and could be really interesting to start. So with that,
So we have no questions.
I interrupted before.
No, it's okay.
I don't want to probably have more technical question.
But do you also plan to go to get some n which is not zero for the pencil selection?
I
I think
mean,
that's trying to fast square.
okay. I think we did for the case also for the stress test. So yeah, we also did for the case of stress test. So in that case, we have n equal to 1. So we have two different possible tensor structure. So in that case, there is not really much difficulty. I mean, there are maybe in the computation, yes, but conceptually is identical. There should be no difficulty.
But in principle, the formula depends on it.
Yeah. For one expression, yeah, for the second simplifying limits, I think it's easier because if you take the leading order and the large separation limit, the dependence on n, you just factorize on the safety data.
I see.
So while if we take before the leading order of the defect type limit, then n enters in the upper function, let's say.
Okay.
So in that sense, it's that's different. No? It's more difficult.
Yes. Okay, there are no more questions. Let's thank Andrea again. 5 minutes break, and then when we change speaker. Yes.
So what do you say?
Sì, sì, sì. Sto vedendo. Vasco, do you want me to come? You know? Yeah, I just, yeah. But, okay, I can offer it to. Okay, I'll leave it with. What we are waiting. So your problems are not energy scales. So you're.
Yeah.
You see the map?
Well,
Can you summarize the meeting, what she said?
One of the main types is, she's asking for the contacts, I said mine.
There is a
Yeah, I guess it's not for you.
I'll give it, okay, I'll reply now.
Okay, or after the talk, yeah.
Okay, I reply at, when we finish at 4 AM.
And we were not considering some scales. The perturbative appears when we solve the puzzle equation that were extracted from blocks. I mean, is it just no,
No,
what sense?
because in the safety, you can record the assignment by applying the essential PMU. That's, you can repackage all of them into some custom equation.
Yeah.
Okay, so you solve that and you just includes into that sum, the primary, not the same. The primary sum of A or the sense of A, are obtained by taking the primary and applying the PMU. So they're kind of trivial in the safety. They just worry about the primary. In general, if you QT, you have to know the PMU and also the Where's the far? Where's the far? Too far. I mean, it's not, our problem is not for QC, but QCD will not. Well, yes, but it's the same idea, but just it's crazy or more powerful because you can use the power loop, but then you something from the beginning.
Yeah, the difference is that in the safety we have a convergent motion for the so we can always like if we have an endpoint function reduced to just a two-point function, which is known, it will be known in the safety data we know all the theories. Which is something that is not we cannot do this in a general KT.
For some quantities, which we have no idea at all, how big they are. Big is our,
Yeah.
formal limit is our house. This limit, this is late.
Yeah,
This
because
is
the formal data is not random, it has to be such that if you take your function, you decompose in the S channel, say, that's equal to decomposing in the T channel by associativity of your field.
Yes, associative.
So that's an equation. Now, that equation is powerful here because you can boil it down to two convergent series. You have left and left. Now, that conversion, I think, is not true for generating S matrix. I can say the same for S matrix, but that's not, you don't have convergence and you don't have this kind of simple function, well, not simple, but hypergeometric type of function that appears here, just because in the S matrix we have logs and stuff, and that's not how it works. So the logs will then become when you sum, get the logs. So here you don't see the map periods like in the what Lorenzo was saying is that if so this function here they're kind of in some sense you can think of them as well when you put the theory the quantitative theory yes some of the machinery survives. And for example, you don't see the logs, but you see something that has poles. And then when you take some limits, these poles will accumulate and generate the logs with the top of this matrix. Yes, so it's the ADS, you get discreteness and then so this machine applies and helps you moving along. But for a straight application to the video case that I have in mind, I have I mean, the best thing is
Any feature or
yeah.
partly, right, or not? Or just property on the post. So we have is where after this PSP function that we have, we extract a piece of kinetic and this part is probably the most important part is it's very important information for us because we have no idea how big is the four big functions. For the PSP function, we have some idea. So if you have this kind of link where something, then
But would it be, I mean, we can have
Excel was formalism up to the end. That's my point. My point is that my problem is that we don't follow the formalism up to the end.
But then, yeah, like Excel was be on top on this twist 3 stuff, we can add tomorrow. You asked around, but nobody was happy to show focus.
You can go or Arturo. Here are what page.
I really asked you because I asked Oscar, when talk.
No,
Pablo, sorry, just, but
no, sorry.
it's not the non-subject. Anyway, let's continue with Lorenzo. With Lorenzo. Sorry, yeah, very much names. So Lorenzo again pitches in Torino, then we talk about postdoc, sorry, my fault, my bad. And we talk about explicit OP, conformal blocks, and Casimir operators for Virasoro CFTs.
Thank you very much, Francesco. And it's great to be here in Madrid, in this beautiful city, to give a talk. And right now I'm going to give a talk which is fairly different from the one that Andrea gave on our project in defect CFTs. This is going to be a very different approach. That it was mostly kinematics, like a lot of kinematics, but mostly towards dynamics. This is basically just going to be kinematics and tailored to two-dimensional CFT. It's fairly technical, I would say, so I'll try to make it as accessible as possible and skip a lot of like the complicated mess. But I invite you to ask questions in case something is not understandable, and I'll try to make it as pedagogical. All right, but what am I going to talk about? I'm going to talk about some results. I got together with my collaborator Jean-François Fortin from Laval University in Quebec City and Vito Schiva from Yale University about some foundational, let's say, representation theoretic objects in Virasoro. So which has to do with two-dimensional conformative theories. So the setup of today is in fact 2D CFTs, which well, it's hard to overstate how useful they can be in the modern theoretical physics to understand various aspects of high energy theory. For instance, they describe two-dimensional physical phenomena, which are sometimes very interesting also from the point of view of experiments. But from the more formal point of view, we care about 2D CFTs. If, for example, we want to describe the string theory with a worldsheet approach, what lives inside of the worldsheet is a two-dimensional CFT, in fact. You can describe some quantum gravity systems in ABS3 by the use of some CFT2 at the boundaries. And last but not the least, CFT2s represent some class of, well, they have some subsector of examples of solvable quantum field theories. So they can really be a nice window towards non-perturbative physics. So that's why we care about 2D CFTs in general. And why are they so powerful? Why people care about them a lot? It's because they are highly constrained. So the symmetry algebra that underlies these theories is known as the Virasoro algebra. It's an infinite dimensional algebra, which given its presence, simplifies a lot the structure of your theory and allows us to understand a lot about it. So what we're gonna focus on today is some aspects of the Virasoro algebra, Virasoro representations, let's say, tailored to what we care about in physics, and see how we could get some new results about this very old subject. So the goals of this talk is basically gonna be to discuss 4 objects that we found the new expressions for, which, as you can see from the names, are fairly basic in the sense of like some objects that we would normally think about, and which is surprising the fact that they were not determined before. People have been working with the Virasoro algebra since the 80s, even earlier than that, and it's, well, it was surprising also to us that we had something new to say to the literature, in the literature. What are these objects? The first of them is an expression for the resolution of the identity, by which I mean you have states, you want to decompose, well, you want to decompose your identity in terms of all the set of states that you can have in your theory. But how do you can write it in terms of some bras and cats abstractly, but what do you put there? It's not so clear a priori. Connected to this, there is the notion of an operator product expansion that basically allows us to replace products of 2 operators with an infinite sum of other operators. But once more, what is it that you put there on those question marks? That's what we care about. And connected to that is the notion of conformal block expansion. So determining one means you can determine also the other. And last but not the least, since in higher dimensional CFT, these concepts, in particular the conformal blocks computations, are associated with some notion of some Casimir operator. One flavorful question we wondered about was whether one could determine some Casimir operator for this Virasoro algebra, and we thus determined some object that actually commute with all of the generators of Virasoro. So these are basically the goals of this talk. It's fairly short in time, so I will not go too much in depth, but I'll try to basically scrape all the nice, interesting details and give you those. But at any point, if there are any questions, please feel free to ask. In order to be all on the same page, I will start with some basic things about the Virasoro, so 2D CFTs. 2D CFTs enjoy 2 copies of Virasoro algebra as a symmetry in themselves, so we can focus on that and think of their representations to understand what kind of objects we have in 2D CFTs. And Virasoro is this infinite dimensional conformal, infinite dimensional symmetry algebra that has this form. You don't care too much about the specific details of it, but you have infinitely many L generators plus 1 C generator, which is known as the sandwich. Okay. In physics, we care about states, we care about operators. So it's interesting to discuss, first of all, what kind of Hilbert space we discuss. We can have what kind of states we can have in our physical theory. And most of the kind of states we can have belong to representations known as Verma modules. If this is the first time you see this term, it may be a little bit scary, but it's actually super simple. We probably were already exposed to that. A Verma module is nothing but a primary state, so some highest weight, some basic object, and the whole tower of descendants that you can construct from that primary state. So you get a primary with a very well-defined conformal weight, with a well-defined central charge associated to it, which is annihilated by all positive modes of the algebra, so highest weight, once more, and acting on that primary with the L's with negative index, you can construct the whole tower of the set. So a Verma module is nothing but this thing, you can do it arbitrarily, you encounter no issues, and that's it. So this is one class of representations in physics that we care about. That we can represent to make expressions a bit more simply with this notation here. So here, an arbitrary state within a Verma module we're going to represent in this form. So L minus mu H, which represents a basis vector in this descendant space, where we decided some ordering of indices in order to not repeat ourselves and in order to have just independent objects. All right, so these states also have an associated level. This is just the sum of all the indices. And this is the way we can describe them. So first class, Verma modules, arbitrary states, we act with arbitrary modes. Second class of representation that we care about, we're going to see soon why we care about both of these things, is the generate representations, which are special representations that occur when your data, your conformal dimension and the central charge, let's say, are tuned to very specific parameters. And in this case, you have basically that some descendant that you can construct with the action of some negative modes, some construction operators, behaves as a primary. Behaves as a primary, what does it mean? It means that if you act with some positive mode here onto your descendant here, you get something which evaluates to 0. This is proportional to L0, which measures the conformal dimension, minus this HRS, which is precisely the conformal dimension of the state. You get something which evaluates to 0. That state is a descendant which is also a primary. It produces a whole tower of states that decouple from your theory you don't care about, and normally you just throw away. All right. Once more, let me build a little bit more notation connected to this, and soon it's going to be clearer why we care about this. You can detect this, the presence of these states by studying what is known as the Shapovalov form, which is another fancier way to say a gamma matrix, so a matrix of scalar products of your states. And whenever these are determined at 0, you basically measure that you have a certain degenerate representation. So you have these special representations occurring at these very special values, HRS, of conformal dimensions. All right. Why do we care about all of this construction? Because, as I promised you, we care about determining something as some resolution of the identity for our representations in 2D CFTs. So what is it that we want to do? We want to have an object that applied to any arbitrary state like this just returns the initial state. Okay, some non-trivial object that does this job. This is interesting because it basically tells us what is the inner structure of representations in this. So the way you should construct them, the way things are reorganized in representations. And why did I introduce you all those terms, that Shapovalov form? It's because it's known in the literature, it's been known since ages, that to determine this resolution of identity, you basically need to have the inverse of that Shapovalov form, of that gamma matrix, contracted with your generators, and this object should behave as the resolution of it. Okay, so in principle, you can say, okay, you have this abstract formula, and it's been known since ages. So what am I telling you? Well, I'm telling you that this formula is not that useful because, as it is, in order to determine some object at a certain level, you need to invert a very large matrix. This Shapovalov form is a matrix whose size grows, let's say, exponentially. It grows with integer partitions. So it's basically a definition that is not so useful to you. So is there actually a better way to determine how these representations are organized?
So just a question, so
Yes.
yes, only within one Verma module, right?
This is only within one Verma module. In principle, if you want the dynamical, say, resolution of the identity, you should improve the spectral density and integrate over the depth, the overall edges.
Another question is, do we do something similar in global similar? Like I could ask, given a formal family of some primary, I want to add some overall descendants and write this. We do it.
You can do that. And in fact, it's something that I'm working on in doing this in 3D CFT more explicitly.
Okay.
Because the abstract formula does apply. You can, in principle, determine this inverse Shapovalov form, and that gives you the contribution of states at that determined level. In, say, 3D CFT, you have two notions of level because you have spin that you can raise and lower, and the conformal dimension you can raise and lower. But the main idea applies the same. Okay, so is there a better way to determine this structure? So basically, can you understand a bit more what's the inner structure in the inner representation? The answer is yes, and it comes from one basic idea. This basic idea is, instead of studying matrices that grow in size and all. We study objects that do not depend on indices, that are not matricial. We basically contract the inverse Shapovalov form, which has two associated indices, the basis of the states at a certain level, with the generators that we have automatically from our algebra. And we can see that this is basically the same combination of objects that appears in the resolution of the identity. So this is kind of some index-free notation that we can use to work with this object. And this object in bold-faced, this index-free thing, actually satisfies some nicer properties compared to the individual matrices. So this is the main aim. Let's study something without indices, because in general, it's always nice to avoid when you can. Great. So this is just one object that satisfies some nice properties because it has to act as a resolution of the identity. So it must have, it's the inverse also of that Shapovalov form that has zeros and whose determinant 1 to 0 in special values. So we know it must have some poles. We know these poles have to be simple. We know how it should act, basically, on a various bunch of states. We know that at large H, all of the properties must still be true. So basically, without showing you the details of the proof, but you can put all of these conditions together and prove by induction a certain form of this inverse Shapovalov form, which is the one presented here. So this is super compact. You can say that at a fixed level, the whole complexity is in combinatorics. And the structure is actually, you have all possible products of these singular vector generators. These LRSs are what produce the singular vectors when applied to the highest weights. And you take all possible orderings of all possible products of these singular vectors, and you basically have some sum of diagonal objects with this form and with specific poles that you would expand on these special representations. So we proved actually that this must be the form. We showed explicitly what have to be the explicit coefficient for all of this. And this basically tells us by just plugging this expression in what I showed you before in the resolution of the identity, the expression of a resolution of the identity within a one. So basically, already at this stage, this is telling us actually any representation, even the ones that are not degenerate, even the ones that do not have these special truncations within their towers of descendants, any representation cares about these singular vectors because it's reorganized in terms of their action. We just act with them a bunch of times to produce the descendants, and descendants are naturally organized in terms of that. All of the coefficients that appear are organized in terms of that.
So can you say again, is the summation index L?
Yes, this L is the level, so it's the sum of all the indices. So it's basically how, if it were higher BCFP, it's how many p's that you're acting with. This R dot S is a way to summarize the fact that we're taking the one L RS has a level R times S. So we have to take a bunch of LRSs whose total level is L. So we see any sum over all possible combinations that you have. Okay, so this is the expression. It seems it's fairly abstract, so let me show one simple example in which you express it and you act with it here in the bottom right. The resolution of the identity acting state on a state with the level 1, which is just one state possible, so L minus 1H, is just reduces to one term, which is this level 1 term, just plugging the definition here. You get a pole, you get a level 1 action on there. You commute generators, L1, L minus 1, the commutator is 2L0. That's an object that simplifies with the pole that you have over there, and you just reproduce on the nodes the initial state. Something similar in flavor to this happens at any level, so this is something that that is quite nice to see in practice, although highly inferior. Okay, why is this nice? Well, first of all, it's some foundational objects. It tells us how things are reorganized, and it allows us also to determine the Virasoro operator productive function, the way it is expressed. what is the OP? The OP, we saw one version of OP today with the boundary OP, but this is just a more classical version in CFD. It's a statement that basically tells you if you consider some, let's say in radial quantization, if you consider some correlator in which you have an insertion of a few operators, you can, as long as you can carve out a circle around the point in which you're quantizing, you can replace the product of these two operators in your correlator with an infinite sum of individual insertions in it. Why is this in any way correlated to what I mentioned before? Why do we care about resolutions of the identity? Well, simply because you can write down the OP in terms of a resolution of the identity, the exact same object that I showed before, the resolution of the identity within another model. The OP is nothing but the sum over your whole spectrum. So this is the dynamical part, and there should be like some kind of density in this expression. And you insert this resolution of the identity times the product of the that you care for. This is a state fixer to describe the operator product expansion. So by having determined an expression for this resolution of the identity, we can just plug it in and see an expression for the Virasoro operator product expansion. Concreteness. We just do that here. I'm just plugging in the expression we determined, and we get some expression reorganized in terms of this quotient, which seems fairly complicated at this stage. We have the same coefficient that we had already determined. We have the action of singular vectors, the singular vector generators there, and here we have the OP coefficients. We can actually further simplify this by noticing that this object that I highlighted here has to give you zeros when you have fusion rules, when you have special representations that combined have to give you, again, some special combinations of fields. So you have some kind of selection rules. These are the fusion rules. These basically constrain you completely, this object here, and this gives you the expression of the operator product expansion. So this, what I'm stating here is that in Virasoro, but since this approach is fairly general in principle in any CFD, the operator product expansion is reorganized in terms of singular vector generators with coefficients that are determined in terms of fusion, which well, everything in front of the singular vector generators here is completely explicit. Let me, this bracket here is determined here, and it's if you're familiar with the Liouville notation, you may know why I'm writing it like this, but it's a very well-defined polynomial of conformal dimensions. So this is an explicit way to write down the operator product expansion in terms of these singular vector objects, which are the only complicated part of the expression. Expressions of these are known in the literature, but they're very complicated. Okay, are there any questions at this stage?
So what determines which modules you will get from the T?
So what determines which Verma module is well, here you have the OP coefficients. This is another way to write them down, to Cij, let's say. So in some cases these are going to be zero. In most cases, let's say, so stuff that don't appear are enforced here in most cases, apart from the conditions imposed by the fusion rules, which are imposed from these coefficients. So these enforce you the fusion rules. So whenever you have degenerate representations combined with something that restrict the possibility of what things you can produce, while here you just have the OP coefficients. I'm not saying anything about the OP coefficient, of course, because I'm staying fully kinematical, but basically what I'm pinpointing is this is the kinematical structure. Okay. Okay. Further questions about the OP? If not, we can move to apply. Yes, please.
This should truncate for minimal models, right?
This should truncate for minimal models. Yes, because you have, if you take like degenerate representations, you have that these things have zeros. And
Yeah, with the numerator. Okay.
exactly in the numerators. So you don't have other representations. Yeah. So that part, that kinematical part actually enforces the fusion rules that are the only thing that are relevant for me. Okay, so we can basically then, having determined the Virasoro B, let's make one step further and let's determine some expression for Virasoro formulas, which are known to be very hard in the literature. What are these objects first? A couple of words. Virasoro conformal blocks are nothing but contributions of a reorganization of a correlator in terms of all the possible representations that you can exchange in an operator product expansion. So you can write down a 4-point correlator of this form, for instance, work out an operator product expansion between two fields, let's say these two over here, and this is going to give you an infinite exchange tower of operators, which basically is exchanged with the other two fields that are in the correlator. And this is a way to express everything in terms of the OP coefficient, these objects that were shown in the previous slide. But another way to represent this is actually conformal blocks are nothing but an insertion of a resolution of the identity within a correlator. So if you represent a correlator in terms of states, where you have where you're evolving from a certain state, which here is H4, towards another state H1, you basically have that conformal blocks are insertion of this resolution of the identity associated with a specific Fermat module. In this case, is the one associated with H. Or in other words, in a more graphical picture, you're gluing two 3-point functions with the use of this glue that is the resolution of them. Okay, is a way to work out 4-point correlators in terms of 3-point correlation functions, which are fully kinematically determined. Okay, so we basically just plugged in whatever we have worked out already, the resolution of the identity. We can see it in this way. You can just plug in a resolution of the identity in the middle of a correlator, divide just by the OP coefficients because we care about just the kinematical part in this case. You get two ratios that are of exactly the same kind that were present in the OP expression. So these are the objects that I mentioned are fully constrained by the fusion rules. So once more, we get something which is fully reorganized in terms of these, and is fully determined, and allows us to express explicitly a series expansion for the Virasoro conformal blocks, which was not previously known in the literature, at least not in this form. There were other forms that derive from, let's say, the AGT correspondence. This is an orthogonal way to approach this type of calculation. So yes, let's unpack a little bit what I'm showing you. That I'm showing you some fairly compact object. What do we have here? We have some series expansion in X. This is just the standard cross ratio you use for 4-point correlation functions. So Z12, Z34 over Z13, Z24. And the structure, what is the structure of this object? It has explicit poles in H, which is exactly what you would expect from, say, if you're familiar with the homological recursion relations, it's exactly what you would determine from that. It has explicit coefficients, once more, determined by the fusion rules, and these Q coefficients, which we have determined in our proof. And you just combine everything, and the whole complexity of this is just repackaged in the combinatorics. This is the only complicated part of this expression. Everything else is trivial. So what is the combinatorics of this? Is once more the whole set of all possible singular vector generators that make up a total level L. Is again this simple symbol R dot S equal to L. If you want to see it in pseudo Mathematica code, what kind of combinatorics is relevant for this? Is you take all integer partitions of your level, you take permutations of those, and then you see all possible divisors to see which singular vectors you can. All right, I'm being a bit abstract here, so let's get a bit more concrete soon. We can actually compare this with stuff that was known in the literature. We can work out certain limits. and see if actually what we had gotten makes sense. Basically, just by imposing some sort of consistency condition, like which is you set one external operator to be the identity, you have that everything should be trivial. And this condition of everything being trivial is actually non-trivial itself. This is this equation here, which by consistency has to be true. And this is actually fairly powerful because it allows us to work with this infinite series expansion and really determine known formulas, at least, for, let's say, for large central charge behavior conformal blocks. If, for instance, we want to work out the global algebra conformal blocks, which are extremely simple, 2F1s, we can just take the, well, B going to infinity here is the large central charge limit. We take the large central charge limit, we plug in this identity that we worked out above just by consistency. And we get on the nose the 2F1s without the global conformal blocks. Furthermore, there are a few interesting limits that you can consider, like semi-classical limits. And you can actually take semi-classical limits within this identity that I'm showing you above and work out some, let's say, leading asymptotics of the blocks of the exponentiated blocks in for Virasoro 2D CFTs. For instance, if you take what I mean here, if you take a large central charge and we consider heavy operators which are proportional to the large central charge, you can work out the same type of steps that led us to the global conformal blocks to give us some exponentiation of some terms in the block expansion, which reproduce exactly what is known in the literature, coming from a very different approach for these semi-classical conformal blocks. Okay, are there any questions? I know it's a fairly abstract talk and fairly technical, but I'm trying my best to keep it down to earth. But the key message of this part is we have a new expression for the Virasoro conformal blocks, which was not previously known. And this is one of the first main results of this new approach, for this new kind of approach to representation theory in CFT that was not done before, which is quite neat.
So maybe you could derive this from some logical recursion, right? So
This, yes. This above, no. This series expansion you could not determine from, well,
it still solves
it still solves some logical recursion, exactly. We did check explicitly that it does solve some logical recursion. You do have to do quite a bit of reorganizing to get this form. So of course we're talking about the same object, but
it looks like a question for AI now that we come back to the discussion of last week.
Yeah. Yeah, I mean, how would you produce that from a recursion relation? Or in some sense, it actually may be interesting to go the other way in higher DCFT, because it's kind of, say in 4D, I think it becomes very complicated to do some logic of recursion because you have a more complicated pole structure. So I do wonder if this approach with this kind of construction of this inverse Shapovalov form can actually lead to something simpler, like the resolution of the identity maybe is somewhat more manageable to produce. And then you would get an expression for, say, spinning blocks, which is more, which is possibly more straightforward than some logical recursion. But okay, take that with a grain of salt because it's not guaranteed that it would be the case. Further questions about the conformal blocks? If not, I would move to the final part, which is Virasoro Casimir operator. And this is kind of an interesting question that we found, kind of a fairly mathematical question, but that we ask ourselves out of curiosity, and it's what sparked all of these explorations, is can you actually determine an object that commutes with all of the generators of the Virasoro algebra, so a Casimir operator from the Virasoro algebra? This is something that was not known in the literature, if there is one, like how to determine one, in particular, an expression for one, say. And you can see that if you do work with standard approaches, such as like the killing form approach to work out the quadratic Casimir, you get something that doesn't make any sense. You get while this approach works beautifully for the global algebra, you get just a standard Casimir operator. This approach does not work for Virasoro. So you get something which, like on the nose, will diverge. You can try to do some zeta function regularization. You will get something which is 0. So the killing form is kind of 0 in this case. What does it mean? Can you even construct this object? Then it is not clear. So this is to say, maybe a priori, someone may even wonder, does it even make sense to expect some kind of object? Well, what we realized, one of the first things that we realized is that, well, there should be something, though, because there should be some object that measures the weight of your whole representations in CFT. So the Casimir gives you an eigenvalue, which is the same for the whole representation in CFT. So there must be something that labels these weights. And furthermore, there's a fairly mathematical argument by which you have some kind of connection with the Heisenberg algebra. We will not go into detail, but you can basically construct from this relation between the two an object that commutes with all of the modes of the Virasoro algebra, just not expressed in terms of Virasoro generator. So it's something that you can map to, that a posteriori you can realize there has to be something that commutes with all of the modes of Virasoro, but it's not so trivial to construct. It's not so trivial to know what this would be. So what we did is just work out an ansatz. This object must be of this kind of form with some matrix coefficients. And we basically have that consistency condition, one post consistency condition of commutativity with the modes of Virasoro to make sure that we can determine this object. We can plug this in the commutativity conditions, and we work out some consistency condition. We can start to solve them and start to be happy because we find something. And then you realize, then what happened to us is that we realized that in the literature this problem was already discussed, because there was, of course, an obscure paper written in Russian with barely any citation by Fagin and Fuchs, though, two very important names, who discussed abstractly some way in which some kind of Casimir operator for Virasoro would have to be. They didn't go too far, though. What we did is basically then use our answers, use the results that we had, use their recursion relation that they had somewhat expressed, and work out in an explicit way this Casimir operator for Virasoro. So this is actually determined in terms of the inverse Shapovalov form. The inverse Shapovalov form is the object that we started with in this talk, so it comes back once more. We are basically milking this object as much as we can over here, but it nonetheless allowed us to determine a fairly complicated object, but that was not previously known the way it's structured. Here, there's again complication in the combinatorics. There's a bit more involved combinatorics compared to before, but it's well, you can ask me about it later. It's just some further permutations compared to what we had before. All right, so we did determine there is some object in Virasoro that commutes with the generators. I promised you some kind of relation that depends just on one level 0 function. What I'm saying is that basically, what I'm saying is basically that there's one free parameter, one free function in this expression that tells you what is the eigenvalue of this infinite order object. And there is actually just one independent Casimir operator that you can determine. Let me just go a little bit quicker in view of time. But yeah, there is just one independent object that you can construct. You can, in principle, reproduce the same, perform the same type of analysis that we did on the global algebra. You can get similar type of expression, but of course, you know, there's just one independent object. And if you specify your eigenvalue to be at 0 times 0 minus 1, you get the standard Casimir. Otherwise, you get something which is generically a function of the quadratic Casimir, which is expressed in this way, in this series expansion, let's say. And what I'm saying here is just, there are just one independent object in Virasoro, you can choose whatever eigenvalue you want. For that, because it's anyway an infinite order object, you're never going to have a truncation. And last but not least, let me just say one last final thing about this object, which is why were Casimir operators important in higher DCFT? Because Casimir operators lead to Casimir differential equations that are some differential equations that you can use to solve for conformal blocks. Here we go in kind of the opposite way. We determine some Casimir Virasoro Casimir operator. In principle, this is associated with some differential equation. In this case, it's going to be infinite order. We could determine this explicitly. Actually, this is not a published result so far. But there is a concrete infinite order differential equation that you can write down. And you can check explicitly that if you plug in the conformal blocks that we determined, the series expansion that we determined, this Casimir operator just gives you the eigenvalue. And that's it. So what I'm showing here is that there's the same type of structure that one has in the higher DCFT of a Casimir operator determining Virasoro conformal blocks, just with a much more complicated case with an infinite order differential equation for which we have explicit solutions, so which is kind of peculiar, I would say. I'm not sure I've ever encountered something like that. So with this, I conclude. This is the last thing that I wanted to say. Just to reiterate, we determined the structure of the resolution of the identity that allowed us to also determine the Virasoro operator for that expansion. We have some concrete formulas for Virasoro conformal blocks in terms of series expansion. And we found out some infinite dimensional Casimir operators for Virasoro, for the Virasoro algebra associated with known eigenfunctions, explicit eigenfunctions. And all of this basically gave us a bunch of new tools for 2D CFTs that now one can wonder how this can be put at use into some, say, bootstrap setups. For instance, using the explicit series expansions for Virasoro to do some kind of analytic bootstrap that would be kind of neat. We worked out some expression of this non-local infinite order Casimir operator, but we don't have an interpretation for that. What is this thing, like even holographically, let's say, what is in ABS, this kind of infinite order differential operator, for instance? That's a question that I would really like to have an answer to. And in principle, our approach was completely general. So, well, it's just applied to the case of Virasoro, but one can imagine doing the exact same steps in other algebras. So this leads naturally to the question: can actually one do this for other less understood algebras, let's say, such as Kac-Moody algebras and W algebras, to work out expressions for Casimir operators, conformal blocks, and all of that? And last but not least, let's say, since we're ultimately living in a higher dimensional world, we may care about explicit expressions for stuff that we can use in CFT. So one thing that I'm wondering about is, can you actually determine explicitly UP for a higher dimensional CFT, say in CFT3, for instance? Thanks for your attention, and yes, it was a pleasure.
Question? Regarding the Casimir, one very important thing you mentioned just that eigenvalue blocks. Another important thing with high dimensions is that it's uplifted to the embedded space where you can also act in EDS, the time level equation, the equation of motion, and act on CFT to use the conformal blocks. Do you think something like this, because you know that the ADS is also sensitive to numbers or order? Is that something that one can think about?
Certainly something that one can think about. I have no idea what's the answer to that, though. What is the uplift to ADS to that? In fact, it's somewhat what I was wondering with one of these steps, like the holographic interpretation of this Virasoro Casimir operator. It's not super clear. It may have to do with this like Chern assignments, like SL2 Chern assignments in ADS3 or like this Virasoro TQFT, but it's not super obvious like what it would be. It would be some kind of object that you can construct there, but yeah, what is it? I don't know. That would be nice. And then need to know.
And also, since you know how the blocks behave, I think it's
I don't know if it's the future generation that's waiting
Mhm.
there. You know how the box behavior, you know how the box behavior is something, you bootstrap the differential equation for when it can be so actually some, you know, there has to be a quadratic equation. You can assume linearity, I think. You can write out when you write a linear combination of differential operators such that it becomes an eigenvalue equation.
But here you don't know that it's a quadratic equation.
Oh,
It's not, it's infinite order.
Oh,
So
yes.
it's, that's the very trivial part of the differential equation. Nonetheless, it's infinite order, but we could show that, well, here I didn't show, I'm abstractly claiming that, that it's the case, but you can actually show it explicitly, that if you apply this differential operator, which is organized as a series expansion in interest ratio, okay, to the conformal box, you basically have some simplification, some identities with these coefficients that appear there, and you just have the eigenvalue. So, yeah, I would say there's not much more one can do. This is fully arbitrary, by the way. This is like you have okay, sufficiently nice functions that give you the eigenvalue. You can choose any sufficiently nice function that determines the eigenvalue, and you have an arbitrary infinite order differential equation associated to that function, and that equation is satisfied by the case. These thetas here are the x dx, like the differential operators. That's
Maybe, do you know if your formula for the Virasoro interpretation on AGT?
I got it. It's another reorganization of the expression again. There, I would argue the structure, the combinatorial structure is fairly different in AGT. You have, well, I don't know if I have anything that's going to make it more clear for the AGT part, but here we have just one sum over this type of combinatorics, which is this R dot S, the whole set of singular vectors that make up a total level. There you have a sum over pairs of Young tableau, which I argue is kind of similar to just plugging in the definition of the original inverse Shapovalov form as a matrix itself. Let me maybe you will. Yeah, there is no. Okay, I'm past that, but yeah, here say each index runs over integer coefficients, so runs over Young diagrams. And in principle, the resolution of the identities are organized in terms of Young diagram, matrix, Young diagrams. If you plug in something with this form, I think you would get the AGT expression in this way. But it must be reorganized in this basis, in terms of this basis. Our expression is reorganized in different ways. So it has to be compatible with that, because it's also compatible with homological, but it's not quite it's not the same yet.
Okay, let's thank Lorenzo again.